So yeah, as I said, we're just going to be kind of talking about these first three, but I would recommend checking out the documentation for how any of these other ones might operate or how you could use them. So the first one is the model, and we're going to set up the same model that we did in the first video. And as you might recall, we had our probability of heads coming from a beta distribution with parameters alpha and beta, and both of those were set to 10, and they were set to constant values, alpha and beta. And our probability of flipping heads was a stochastic node. And then we said that we flipped the coin 10 times each time we recorded the number of heads. And then we said that x was the number of heads that we recorded, and that came from a binomial distribution with parameters p and n. And we can see that x has, in this case, a value 7. But what we want to do is we want to attach some data to this x node, and we can do that with this clamp method. So let's say we wanted to attach, let's say we actually had 3 heads, and we wanted to attach it. So now if we look at x, it's 3, so we can use this clamp method to attach data to a node. Now, our x, as you might recall, is just a single value, but we had a bunch of data because we flipped this coin a bunch of times and we recorded the number of heads a bunch of times. So to do that, we're actually going to have to use a for loop to clamp multiple data items. So for I in 1 to 100. And then in this case, we're going to say x is a vector. So we're going to say the ith value of x comes from a binomial distribution with parameters p and n. And then what we want to do is that ith value of x, what we're going to do is clamp it. And we are going to clamp the ith value of data. And this data is that data that we simulated earlier. And then all we have to do is close our for loop. And all of our data is attached to an x node. So then to finish up making this model, we'll make some variable, we'll call it my model, and we'll use this model function to ramp everything up in a model. And all we have to do is put some node in our model in this model function. So in this case I chose p, but I could have put alpha, beta, n, or one of the x's in there. So now we have my model, and we can type my model to see what there is, and it'll print out all of the nodes in our model. And in this case, we're looking at x of 100, and we can see some information about it. We can see the value, what kind of node it is, what kind of distribution it comes from, whether it's clamped or data is attached to it, what the log likelihood of that node is, and if it has any parent nodes or children nodes, we can see those as well. So this is kind of useful to see whether our model is set up correctly. Okay, so that's our model. Next up are the moves, and we need a vector of moves, and in this case we'll say that the first value of that vector is going to be a slide move. This is the same move that we performed in the last video, where we're just kind of picking from a uniform distribution and adding on that value. So we're going to perform this move on the p node. This is how we're going to move this value around in the parameter space. And then delta, all this is just the size of that window that we propose. And then weight equals 1. And this just says that on average, we will perform this move once per iteration. So this is the only move we're going to actually put into our MCMC. Now, one thing I want to just note is that if we go to the documentation page in the RevBayes website, we can scroll down to a section labeled moves, and we can see that there are a bunch of different moves to choose from, both on continuous nodes or on trees even. So there's a lot to choose from, and we can learn a little bit about the moves by clicking on it. So here we can see the arguments that it takes, and as we can see here, this is the node that it performs the move on. Delta is the window size. Tune, this is something that we didn't put in when we built this, but it is it takes a Boolean value and it defaults to true. And this just says whether we want to change the window size so that it achieves some optimal acceptance ratio. And then there's this tune target, and this is the acceptance ratio that it tries to achieve if it does, if we do tune it. So we can, maybe for our MCMC, 0.44 is an okay value, but if we wanted to make it so that we adjusted this delta value, or if we tuned this delta value such that, we had an acceptance ratio of 0.25, maybe that was more efficient for our purposes. But in this case, 0.44 seems to be fine. But anyway, we can pick a tuning target as well. So these are kind of important things to kind of think about as you're setting up your MCMC, so that way it runs efficiently. So back to here. So yeah, as I said, this is going to be the only move we're going to concern ourselves with for the moment. And the last thing are the monitors. So in this case, we're going to do the same thing where we set up a vector, except it's going to be of monitors. So we're going to make a variable called myMonitors, and we're going to set up a monitor, mn model. And this function, all it does is this creates how we record our MCMC to a file. So the first variable that it takes is a file name. So we're going to call it binomial mcmc.log. And then we will have a print gen. And this just says how often we record into file. And this says that every 10 generations, we will record a value into our file. And then we will have a separator. And this just says that in our file, we separate all of our columns with a tab. And then lastly, I'm going to have stochastic only equal true. So this says that when we record into file, we're only going to record our stochastic nodes that we're interested in this case, the P. And then we can save that. And then we will actually make another monitor. We're going to call it myMonitors2 is equal to mn screen. And then in this case, we're going to give it again, print gen equal to 100, and then P. So what this one does is that as we're running our MCMC, we're going to print out what our MC is doing to screen. So on this terminal here, it's going to print out some information about P. And it's going to do that every 100 generations. So those are our two monitors. And then to make our analysis, all we have to do is use the MCMC function with myModel, myMonitors, and myMoves. And now we have our analysis and our MCMC object. So with that MCMC object, there are a few things we can do with it. There are some methods for it. I'm going to be talking mostly about these first three. This run, this is how we actually perform the MCMC. Then there's also burn-in. This is if we want to tune our parameters or get a good starting point for our MCMC. Then there's operator summary to see how our moves are performing, whether they have an ideal acceptance ratio, or if we have, or if they're being used enough, if they have the correct weight. So this is good for kind of getting some of that information. It also has these two, which are good for kind of if you want to pick up a run, if you had to stop it at some point, or if you wanted to stop it to assess convergence and you realized it didn't converge, so you want to run it a little bit more. These are good for starting a run from a certain place. And I'm not going to talk a whole lot about these, but it's good to know that they're here, and you can check documentation for how to use these a little bit. So now all we have to do is we made our analysis. One good thing to look at is if we do that operator summary, and this is a little, I'll try and make it a little bit nicer to look at. Here. Just gonna zoom it out a little. Okay. So in this case, we can see that when we did this operator summary, we can see the name of the move. In this case, it's a sliding. We can see what operator or what node it operates on. In this case, P. We can see the weight, how many times it's tried, and how many times it's been accepted. And these should be 0 initially because we haven't run anything. We can see what the acceptance ratio is and the parameter. If there is one that gets tuned, what that parameter is. In our case, delta would be tuned if we do tune it. So now what we can do is if we want to tune our parameter, we can do burn-in, and we can do run it. We can run this for, let's say 10,000 generations, and then we can set a tuning interval, and we'll do that at 100. And so this says we're going to run our burn-in for 10,000 generations, and then we're going to, every 100 generations, we are going to try and tune our delta here, in this case, to achieve our acceptance ratio of 0.44. So we ran that, and we can look back at our operator summary. We can see that we tried this move 10,000 times, and we accepted about 4,400, and we have an acceptance ratio of about 0.44. But you can see that our delta changed a little bit. In this case, it got a little bit bigger to 0.00012, and it did that to try and get an acceptance ratio of 0.44. So after we have an acceptance ratio that we're happy with and we have our moves tuned, we can then run our analysis. So all we have to do there is just run, and then we have to just input how many generations we want to run it for. So in this case, we can do it for 100,000, and we can run it, and we can see, well, on the right here, we can see an ETA, and that's slowly going down. And this one actually runs pretty quickly. But then you can just see some good information printed to screen. And I guess one that's kind of nice to see is what this value of P is and where it's at and how it's kind of moving throughout parameter space as we're going through our generations. And then we can see iteration here way on the left. It's printing out every 100 like we said in the MN screen. So this is kind of a good way to look at your run as it's running. And yeah, so now in the next video, we can try and visualize this MCMC output and then assess whether it converged or not and see what our inferred value of P is. So yeah, thanks.